All right, Applied Math. Today we are going to look at a concept called depreciation. Specifically, we're going to be looking at linear depreciation. There's a few different ways to look at it. So what is depreciation? When you own a car, that car has a value. Like for those of you that drive to school, if you wanted to sell your car, you would have some value in mind, whether it's a brand new expensive car or some hunk of junk that you've been driving around for a while. So when the car loses value, that's called depreciation. And it's true for most cars, unless you're talking about like a classic collectible car. When you buy a car, it has more value than when you get rid of it a few years later, because the age of the car is getting older and you've also put more miles on it. So it's just worth less money. Most cars are. So we're going to look at linear depreciation. So this is not the most accurate method of calculating depreciation. It's not bad, but it's not the most accurate. But it is the simplest, and it gives you a good idea of the value of a car over time. So where we're going to have trouble with this is at the endpoints. Like not finding the endpoints of our lines, that's not too hard, but the linear depreciation does not really take into account the fact that cars lose a lot of value right at the start. Like if you buy a brand new car and as soon as you drive it off the lot, you lose like 25% of the value right there. Like you don't even have to put a mile on it and it's already a quote unquote used car and it's lost a whole bunch of value. And then the other place where linear depreciation has trouble is towards the other end, because it assumes that the price of the car is going to go to zero. But in all actuality, the price of a car never goes to zero. You can always sell it for, scrap metal at least, get a couple $100, and that doesn't matter how old the car is. So this is where linear depreciation kind of falls apart. But in the middle, like in the normal lifespan of a car, 3, 5, 7 years, it's pretty good. It gives us a pretty good idea of the value. So just the endpoints we have to be a little bit more careful on. Okay, so let's say we get a car and we buy it for $27,000 brand new. According to the research that we've done, the car will lose all of its marketable value, meaning it's going to be worth junk, after 12 years. So if the car depreciates in straight line form, what are the intercepts of the depreciation equation? So remember from Algebra 1, the intercepts are where we touch the coordinate axes. So the y-intercept is where we're touching the y-axis, meaning there's no x value. X is 0. We haven't moved left or right. So wherever we're touching there is the y-intercept. And also wherever we're touching the x-axis, meaning that y is 0, like we're not moving up or down at all, that is the x-intercept. So the nice thing about straight line depreciation is that it's really easy to calculate those intercepts, and then that means that it's really easy to get the equation of the line. So when we buy the car, our time, which we'll represent it in years for now, that'll be x, and y is the value. It's how much money the car is worth. The car has the most value when you buy it, and this is at the time 0. Like when the day I own it, I've had it for 0 years, and it's worth $27,000. That's what I bought it for. So that can be represented as the point 0, 27,000. That is the y-intercept. The car has no value, at least according to our exercise here. That's not exactly true. This is where the straight line depreciation falls apart. But for our purposes, we're going to say that the car has no value after the maximum lifespan. So that's 12 years in this case. So this is the point 12, 0. So that says after 12 years, we have 0 value. These are the intercepts of our equation. And with those intercepts, we can actually graph a line. And that's what this line would look like. Over here, we've got the point 0, 27,000. And over here, we've got the point 12, 0. So over the course of the life of our car, the value is going down. As we drive it more, as it gets older, the value just keeps going down. Now, let's find an equation for this line. You may remember something called slope-intercept form from Algebra 1. It looked like y equals mx plus b. So m was the slope, and b was the y-intercept. So this one over here on the left. And if we know both of those, then we can write the equation of a line, and using the equation of that line, we can find any point on this line. So if we wanted to say, what's the value of my car going to be after 4 years? We'd be able to go ahead and pull this up here in this equation and find what that value number is right there. Okay, so to do that, we need to find the slope. And slope is always rise over run, meaning the up and down value divided by the left and right value. So change in y value, that's my up and down, divided by change in x value, that's my left and right. So my up and down, my rise, we went down 27,000. So starting at this point over here, 0 minus 27,000, we went down 27,000. My change in x, my run, we started at 0 years and we moved over to 12 years. So 12 minus 0, we get a positive 12. And from there we can divide. And this divides into a slope of negative 2,250. And our y-intercept is 27,000. That's the maximum value of the car at year 0. So our y value here, or our equation I should say, is y equals negative 2,250x plus $27,000. And one way that we can read this is that the car starts at $27,000 and it loses $2,250 worth of value every year. So every year we move along here, we lose $2,250. And we can plug in any number for year here for x, and we can get an exact value out. And in fact, that's what we're going to do right now. We want to know how much this car will be worth after 66 months. Now, our equation, this time our x is in years. So we're going to have to adjust that. We know that there are 12 months in a year. So instead of having an x of 66, we're going to have an x of 66 divided by 12. So we plug that into our equation. We get y equals negative 2,250 times that 66 over 12 plus 27,000. So we can use a calculator. Don't do this by hand. I don't do it by hand. So using a calculator, our car is going to be worth $14,625 after 66 months, which is 5.5 years. So after 5.5 years, our car has lost about half of its value, pretty close to half. I think exactly half in this model, because it's a 12-year term, would be 6. So we've lost a little bit less than half of our value here. Okay, here's a couple for you to try. So the first one, a car sells for $18,495, that's the max value, and straight line depreciates to 0 after 9 years. So in the box here, write the straight line depreciation function for this car in y equals mx plus b form. So you're going to have y equals whatever your slope is times x plus your intercept. That's what your box should look like. All right, so let's go through this and see if you got it. So the y-intercept is the car value at year 0, the maximum value. Since we bought the car for $18,495, that is our y-intercept. The slope is how much we went down in value divided by how many years we moved forward. So negative 18,495, because we're going from that max value all the way down to 0, and then we went forward 9 years. So we divide that out and we get negative 2,055. So that means finally the equation that we're going to use is y equals negative 2,055x plus 18,495. So what this says is that our car has a value of $18,495, and every year we drive it, it loses $2,055 worth of value. Okay, here's another one for you to try. So this time I'm going to give you the equation. So the straight line depreciation equation for a car is y equals negative 4,000x plus 32,000. And we want to know, in how many years will the car lose 25% of its value? So we've got 100% of the value the day we drive it off the lot. When have we lost 25% of that value? Okay, here's how we can figure this out. So we need to figure out what 75% of the car's value is. Because if we've lost 25%, that means that we still have 27% left. Or I'm sorry, not 27%, 75% left. So we need to find that, and we need to plug that in for y. The original value was $32,000. So if we use 0.75 times $32,000, we want to know when our car is going to be worth $24,000, because that's when it's lost 25% of the value at that point. It's gone from $32,000 down to $24,000. And to find that, we just put it into our equation for y, because y is our value. Okay, so 24,000 equals negative 4,000x plus 32,000. And we need to solve for x, because x is the number of years. So if you subtract 32,000 from both sides, you get negative 8,000 equals negative 4,000x. And then if you divide both sides by negative 4,000, you get x equals 2. So that means that after 2 years, this car will have lost 25% of its value. All right, one last thing I want to look at here is what's known as an expense function. So the ones that we looked at before were depreciation functions. The number was going down. What we're going to look at now is the expense, how much we have paid into a car. So that means it's going to be going up. So we're going to simplify this again. This isn't exactly how this works, because obviously you have things like maintenance. You put gas into the car, so that's important too. But we're just going to assume that our only expense in this car is the monthly payment and the down payment. So the y-intercept, so x equals 0, is the down payment. That's how much money we have to put on the day we buy the car. The slope is the monthly payment, but because we're talking monthly payment, we need to be careful, and we need to have our x be number of months instead of number of years. If we wanted to calculate a yearly payment, we could still keep our x in years. Okay, so y equals our monthly payment times x plus our down payment. That's going to be our equation of the line. Unlike depreciation, we've got a positive slope here. We're paying in money, so the line on the graph will increase. How much we have paid over time will go up. Okay, so let's look at an example of this and how we can compare this to the depreciation function. All right, so Celine bought a new car for $33,600. She made a $4,000 down payment and pays $560 each month. She will have the car paid off in 5 years, so she's got a 5-year loan. She knows that the car will have no value after 10 years. All right, so we're going to actually make 2 lines here. We're going to make the straight line depreciation, and we're going to make the straight line expense function. So we're going to let our x be months this time. Because we want to put these on the same graph, we need our x value to represent the same thing. If we've got one of these in years and one of them in months, then our graph is not going to look right. So we're going to let x be months. Okay, so the slope of our depreciation function, we need to find that to get that equation. Our value went down by $33,600, and 10 years is when the car will have no value, and that's the same thing as 120 months. So we've moved forward 120 months. So that means that our slope in our D equation is negative 280. Our E equation, our expense equation, we know all the pieces to that. Our monthly payment is $560, so that's the slope. And our down payment was $4,000, so that's where we're starting. For our D equation, we've got all the pieces for that now too, that we found the slope. So our slope is negative 280, meaning that our car's value is decreasing by $280 every month that we drive it. And our car's value started, or I should say Celine's car value, started at $33,600. So it starts at the top and it's only going to go down from there. And we can graph both of these because we use the same X. We can put them both on the same graph and we can see some interesting things. So this red line is the depreciation. We start at $33,600, and after 120 months, our car is worth zero. Over here, the blue line, we're starting at $4,000 at zero because we put a $4,000 down payment in, and then every month we're going up $560 until finally we've got it paid off, meaning we've paid in $33,600. So an interesting thing to look at is actually where these two equations cross. And we would need to use a system of equations to find this, so I'm not going to get heavily into that here. But just as a conceptual idea, where these two lines cross is where we've broken even. If we were to sell the car here, which looks like it's about 3 years, right around 36 months, then we would have paid in exactly as much into the car as we would expect to get out of it. So we would owe nothing. We wouldn't make anything either. We would break even. Now, over the long run, owning a car loses you money. And that's okay. Like, I need to drive a car to work. So if it loses me money, that's just part of having a job. You're going to have the same thing unless you work from home and you just never drive anywhere. Transportation is an essential expense. Going back to chapter 1, essential versus discretionary expenses. Transportation for me, because I have to drive to work, is an essential expense. So it's okay, but it is something to realize. Unless you're driving around like a classic car that's going to gain value, like a 57 Chevy or something, then your car is going to lose money over time. So the longer we go, the more we lose. We stop paying in after 5 years, but we still keep losing money. And that's okay, but it is something to realize. Anyway, that's all for this video. If you've got any questions over it, ask in class tomorrow, and I'll see you then.